Now let us have this Heisenberg's uncertainty principle as a consequence of de waves, and this Heisenberg's uncertainty principle can be achieved by taking the help of this de Broglie wave concept, that a particle in motion can be taken as a group of waves, and the group velocity being equal to the particle velocity, which we have already proved. Now, as a simple case, as we did it in the previous video as well, if I take a wave of displacement equal to a cos omega 1 t minus k1 x, and y2 equal to a cos omega 1 t k1 x. This is the set of two equations that we have used in some previous video to develop the expression for the group velocity. And finally, the result of that video was that it was found that the group velocity is equal to the particle velocity. And in these two equations, if I consider this as equation 1 and this as equation 2, this omega 1 by k1, or omega 2, so this is 2, omega 2 and k2, the ratio between them gives us the measure of the phase velocity, because the phase velocity is omega by k. Right? So if the resultant of these two waves was y, and that was y1 plus y2, assuming that these two waves are in same phase, they have a constant amplitude, or they have the constant phase. So applying superposition principle, we have y1 plus y2. If you rightly remember, we had the final solution by solving these two equations was this y was 2a cos of omega t minus kx, then cos of del omega by 2t minus del k by 2x. This was the result of the superposition of these two waves, where we had assumed that this omega is omega 1 plus omega 2 by 2, and k is k1 plus k2 by 2, and this delta omega is omega 1 minus omega 2, and this delta k is k1 minus k2. So the resultant of these two waves, if we have to draw that, we have a resultant, and that's can be drawn like this. Okay. And between the nodes, we have the group of waves, and the velocity with which this wave travels is equal to that of the velocity of the particle with which this particle is moving on. So this, up to now, everything is clear to us, and we know the meanings of all the symbols that are used here, and we understand that this group of waves, they exist between these nodes of this wave. Now, that means I can say, in other words, that we can find the probability of finding this particle is between these two nodes. So particle is somewhere between these two nodes. So that's the kind of case that I'm trying to put here. So if I have to use the mathematical condition for this, for the node, what should I presume for this term? This cos of del omega by 2t minus del k by 2x. It must be equal to 0 at nodes. That should be the case. So under which conditions this cos of this whole thing should be equal to 0? That should be cos of that should be cos of pi by 2, 3 pi by 2, and so on and so forth. So we can generalize this thing as cos of 2n plus 1 times pi by 2. So the condition for these two nodes can be achieved by this equation. So here we can replace the cos, and what we will obtain is delta omega by 2t minus delta k by 2x. Now this is my this is my x here. So for these two nodes, what should I use for x here? For x, I will use x1 for the node 1. For the node 2, I will use x2. So if I use here x1, so I can think of this equal to what's called as 2n plus 1 times pi by 2. Right? Now I'll have another equation for another node that will be delta omega by 2t minus delta k by 2. For that, the position will be x2. Now between this x1 and x2, there is now the difference between x1 and x2 will give us the measure of that uncertainty, and this will be 2n plus 1. It will not be 1 now, it will be 3 times pi by 2. Right? Now, in order to get this delta x, I would like to subtract these two equations. So on subtraction, what am I going to get is this delta k by 2 times x1 minus x2. This will come out to be pi. Now, what is this x1 minus x2? So it's the position from x1 to x2. It's the node 1 to node 2. So this x1 minus x2 is going to give us the measurement of the position of the particle, right? So for this x1 minus x2, I'm going to use what's called as delta x. So this delta k by 2 dot delta x will be equal to pi. Okay, so we can think of taking this this k. What's k? K is basically 2 pi by lambda, right? And I can write here de Broglie equation for lambda is it is h by p. So h will be here and p will be here. So what about delta k? What will be delta k? Delta k will be 2 pi. They are the constants. H is a constant. I will have delta p. Right? So I can think of using this, say 2 and this is 1. Using this 2 in 1, what am I going to get is instead of delta k, I will use 2 pi. 2 pi by h delta p. So here it has its own 2. Delta x is equal to h. Okay, is equal to pi. Sorry. So this h can go here. This pi and pi will cancel. This 2 and 2 will cancel. So what we are going to get is delta p delta x is equal to h. So this is my Heisenberg's uncertainty principle, and this delta p is here basically the fundamental error in the measurement of the momentum, and in this equation, the equation that we have achieved here is purely, it's very elementary, or I should say it's purely elementary. if we consider a group consisting of large number of waves of continuously varying frequencies, we will get the product of this fundamental error in the measurements, like delta p and delta x. It will come out to be greater or equal to h cross by 2. And this h cross, I would like to note down this h cross is h by 2 pi, and this h is 6.62 into 10 to the power of minus 34 joules, and this h cross, the value is, value is 1.054 into 10 to the power of minus 34 joules second. Okay, so this way, what we have achieved this Heisenberg's uncertainty principle spontaneously by making use of de Broglie matter waves, and considering the simplest case, and superimposing these waves, and achieving the result of Heisenberg's uncertainty principle.